Today we'll be talking about power cycles, and a power cycle is just one type of cycle that we'll analyze in this class, and it's a cycle that transfers heat from a high temperature source to a low temperature source and converts some of that thermal energy into usable work. So we've got a high temperature reservoir and a low temperature reservoir. So what's a thermal reservoir? A thermal reservoir is a body that's able to absorb a lot of heat or release a lot of heat without changing its overall temperature significantly. So for example, your high temperature reservoir might be a coal burning source or a nuclear source or geothermal source, something like that. And the low temperature reservoir, well, in this case, since you're dumping heat into it, we would refer to it as a heat sink. So the atmosphere, big body of water, things like that, that could serve as a heat sink. That would be your low temperature reservoir. So here we're looking at our cycle right there in the middle. We're going to analyze it like a black box, meaning that we don't really care about the individual processes that make up the cycle. All we're worried about is the Q ins going in, so the Q ins, the Q outs, the work ins and the work outs. So we've got heat being transferred from that high temperature reservoir, that's our Q in, and we've got heat being transferred to the low temperature reservoir, that's our Q out. And sometimes we'll refer to that Q in as QH because it's coming from the high temperature reservoir, and sometimes we'll refer to that Q out as QL because it's going to the low temperature reservoir. Your book, I believe, writes it as QC, so C for cold, but I'm more in the habit of keeping that syntax Q out. And QL, or QL referring to the low temperature reservoir. All right, and at some point in this cycle, during one or more than one process, you'll have to add some amount of heat, some amount of work to your system. So that would be your work input, and then you'll have a work output. That's the whole point of a power cycle, is to get power or work out of it. And for a power cycle, your work out should be bigger than your work in, and we've referred to that as work net out. Keep in mind, we're using subscript analysis, so all of these terms should be positive quantities. Your book refers to the work net out as work cycle. I like to explicitly say work net out because I think it gets a bit confusing when they go on to talk about refrigeration and heat pump cycles, and they call work net in work cycle. So I want to be explicit and not get those things confused. All right, so we need some way to describe how well that power cycle is doing what it's supposed to be doing. How well is it converting thermal energy into work? So for this, we use the thermal efficiency, and it's what you get out of it, what you get out of the cycle over what you have to put in. So what I get out of it, or what I'm interested in, is the work net out, and what I have to put into it is the Q in. Now keep in mind that for any thermodynamic cycle, the work net out is equal to Q net in. And so not just for power cycles, but any cycle. So that Q net in can also be put in terms of Q in minus Q out. And so you can also put this as 1 minus Q out over Q in. That thermal efficiency can be expressed as a percentage because when you plug in the numbers, you'll get a 0 point something. So you can leave it as the 0 point something, or you can express it as a percentage. There is a limitation. It doesn't, you won't go to 100%. There is a limitation on the thermal efficiency for cycles, and that's dictated by the second law of thermodynamics, which we'll talk about in a couple of segments. But just keep in mind that if you calculate a negative number or you calculate something greater than 100%, you've done something incorrectly. All right, so even though we're analyzing this power cycle as a black box, keep in mind there is something going on there. So this is an example of one type of power cycle that you might have. This is a steam cycle, otherwise known as a Rankine cycle. It's very commonly used. This is a simple cycle here. And the working fluid is water, and that water is just circulating through a big old loop. So it starts out at state 1 in a liquid phase. It passes through a pump, and that pump compresses it to a higher pressure. That requires some amount of work input on your part. So there's your work in. Then it passes through a heat exchanger where you add heat. Maybe it's a coal burning source or a nuclear source or a geothermal source or a solar source. That's your Q in coming from a high temperature reservoir. Now you've got this high temperature, high pressure water, and it passes through a turbine. It expands over those turbine blades, causes them to rotate, and you get work out of it. Now your water comes out at state 4 and it's cooled down, but you want to cool it down all the way to state 1 to complete your cycle, to complete that loop. And for this, you use another heat exchanger. This is an indirect contact heat exchanger. We've talked about those. So you've got a colder fluid circulating in that little zigzag loop. And that colder fluid carries heat away. That would be your Q out. So it carries heat away from that primary loop. And so your water, as it passes over those cooling coils, it condenses and its gravity fed out the bottom all the way to state 1. So that's one example of a power cycle. There are lots of other power cycles, but just, that might help you kind of keep in mind what's actually the point of that box. What is that box? So there is something going on in that box, but like I said, in this class, we'll just analyze it as a black box. All right. Well, I hope that was helpful, and thank you for watching.